Warm greeting and welcome to one and all to the second lecture on Unit 5 Laplace Transform. This is Dr. S. Ramya presenting for you. Today in our lecture we are going to see Laplace transform of standard functions such as exponential, trigonometric, hyperbolic and polynomial. And also we are going to see Laplace transform of two special functions, unit step function and unit impulse function. Here we start with Laplace transform of the exponential function L of e power at. And to prove this, we are going to use the definition of Laplace transform. Taking the definition of Laplace transform and applying it for our function e power at, we get L of e power at is equal to integral 0 to infinity e power minus st e power at dt. Integrating this function and substituting the limits, we get the answer as 1 by s minus a. Similarly, we can prove that L of e power minus at is 1 by s plus a. Next we proceed to trigonometric function L of sin at. Again we prove just by using the definition of Laplace transform. Applying it to our function sin at, we get L of sin at is equal to integral 0 to infinity e power minus st sin at dt. Using the formula integral e power x sin bx dx, we integrate and write it as e power minus st by s square plus a square into minus s sin at minus a cos at between the limits 0 to infinity. Applying the limits, we get the answer as a by s square plus a square. So L of sin at is nothing but a by s square plus a square. Similarly, by using the formula integral e power x cos bx dx, we can find the Laplace transform of cos at. This is nothing but s by s square plus a square. Next we move to hyperbolic function sin h at and cos h at. We all know that hyperbolic function can be written in terms of exponential function. Sin h at is nothing but e power at minus e power minus at by 2. So Laplace transform of sin h at is nothing but Laplace transform of e power at minus e power minus at by 2. Here we make use of the linearity property of the Laplace transform and split and write it as 1 by 2 times L of e power at minus L of e power minus at, which is nothing but 1 by 2 times 1 by s minus a minus 1 by s plus a. Simplifying this, we get the answer as a by s square minus a square. L of sin h at is nothing but a by s square minus a square. Similarly, by making use of the formula cos h at is equal to e power at plus e power minus at by 2, we get the Laplace transform of cos h at as s by s square minus a square. Proceed to find the Laplace transform of a polynomial t power n. To prove this, again just we are going to use the definition of Laplace transform for our function t power n, which gives integral 0 to infinity e power minus st t power n dt, which is nothing but gamma of n plus 1 by s power n plus 1. Here we have made use of gamma integral 0 to infinity e power minus a x power n dx is nothing but gamma of n plus 1 by a power n plus 1. In other notations, it can be written as n factorial by s power n plus 1. Gamma of n plus 1 is nothing but n factorial. Hence, L of t power n is n factorial by s power n plus 1. Proceed to see the Laplace transform of two special functions. We frequently encounter functions whose values changes abruptly at specified values of time. For example, when a voltage is switched on or off in an electric circuit at a specified value of time t. The value of t is equal to 0 is usually taken as convenient time to switch on or off the given voltage. The switching process can be described mathematically by the function called unit step function, otherwise known as Heaviside function. The definition of unit step function goes like this. The unit step function is denoted by u of t and it is defined as a piecewise function u of t is equal to 0 when t takes the values less than 0 and u of t is equal to 1 when t takes the value greater than 0, and its graph is represented as given. Next we proceed to define shifted unit step function. In many circuits, waveforms are applied at specified intervals other than t is equal to 0. In such a case, we define the unit step function as shifted unit step function, and the definition goes like this. U of t minus a is equal to 0 if t takes values less than a and 1 if t takes values greater than a. Next we proceed to find the Laplace transform of unit step function, which is nothing but L of u of t is integral 0 to infinity e power minus st 1 dt by the definition of unit step function along with the definition of Laplace transform. Integrating this, we get the answer as 1 by s. Also, we find the Laplace transform of shifted unit step function. Again, by using Laplace transform definition and shifted unit step function definition, we have L of u of t minus a is nothing but integral a to infinity e power minus st 1 dt. Integrating this, we get the answer as e power minus as by s. Unit step function dealt with function whose values changes abruptly at specified values of time. We can think of them as switches changing the forcing function at specified time. This will really not help to the forcing function that exert a large force over a small time frame. For example, striking an object with a hammer or a short circuit in the electrical system. The Dirac delta function or unit function, impulse function, is used to deal with these kind of forcing functions. And the Dirac delta function or unit impulse function is denoted by delta of t minus a, and it is defined as delta of t minus a is equal to infinity when t is equal to a and 0 when t is not equal to a. Dirac delta function is a function that is 0 everywhere except at one point, and at that point it can be thought of as either undefined or as having an infinite value. The Dirac delta function satisfies these two conditions. Integral a minus epsilon to a plus epsilon delta of t minus a dt is equal to 1 for epsilon greater than 0, and integral a minus epsilon to a plus epsilon f of t delta of t minus a dt is equal to f of a for epsilon greater than 0. The integrals in the first and second property are actually true for any interval containing t is equal to a, provided it is not one of the endpoints. Though there can be no proper function satisfying these conditions, we can consider delta of t minus a as a limiting case when epsilon tends to 0 of the function delta epsilon of t minus a, which is defined as 1 by epsilon when t takes the values between a to a plus epsilon, otherwise 0. Despite the strangeness of the function, it does a very nice job of modeling sudden shocks or large forces to a system. To see, we now proof of the second property. If f of t is a continuous function of t at t is equal to a, then integral 0 to infinity f of t delta of t minus a dt is equal to f of a. And the proof goes like this. Integral 0 to infinity f of t delta epsilon of t minus a dt is nothing but integral a to a plus epsilon f of t 1 by epsilon dt by the definition of the function delta epsilon of t minus a. And by using mean value theorem for integrals, this integral is nothing but a plus epsilon minus a into f of theta, where theta is a value between a and a plus epsilon. By allowing epsilon to become 0, we get the value of the integral as f of a, and this proves the property. The Laplace transform of Dirac delta. Next we proceed to find L of f of t. By the definition of Laplace transform, L of f of t is 0 to infinity e power minus st f of t dt. So L of delta of t minus a is integral 0 to infinity e power minus st delta of t minus a dt. Just by using the property which we proved previously, we get the answer as e power minus as. And that gives Laplace transform of Dirac delta function is e power minus as. Thank you very much. Keep watching.